Alright, welcome back. This is unit number 3, and we're doing video number 2, and this one's all about pipes. And so you did some experimental work with pipes. You had straws and discovered that the short straws produce high frequencies and the long straws produce short frequencies. And so you did some investigations there, and we want to start talking a little bit about the theory behind why does it work that way. And so here we go. We have two types of pipes. Pipes that are going to be called open tubes, and then pipes that are going to be called closed tubes. Simply, an open tube is basically a tube that's open at one end and open at the other end. So it's open at both ends. If I close one end, alright, so put my finger over the end of one of them, then we consider it a closed pipe. Now some people hear the word closed pipe, then the whole thing is closed, and that's not correct. A closed pipe is just closed at one end. Alright, so here we go. I'm going to move along pretty quickly through this. So an open tube is a column of air that is open at both ends, okay? And we're going to try to go ahead and illustrate what this actually looks like. And so on an open tube, well, it'll be open over here and then open over here as well, so open on both sides. What actually happens is, if you were to look at air molecule way over here, and air molecule right here, and air molecule way out to the left-hand or right-hand side, those three molecules are going to be doing different things. This guy here is going to be literally moving back and forth all over the place. So as sound is produced, really what's produced in there is going to be a standing wave. That molecule just moves back and forth all over the place, and so does this one. This molecule just moves back and forth, back and forth, back and forth, back and forth, back and forth. This guy actually doesn't move at all. He's basically at rest. So any molecule that's kind of right here is basically at rest, and that's what I'm going to put. So I'm going to go at rest, and then over here I'm going to put maximum displacement. Maximum displacement. I'm going to kind of zoom in a little bit so you can actually see it. So maximum displacement over there, so it's moving back and forth quite a bit. And then over here, I'm going to put maximum displacement as well. Alright, so what is that? Well, I guess let me back it up just a little bit here. Okay, it's kind of tough to illustrate these little dots, it's hard to illustrate this air in this tube with little bitty dots all the time. And so we're going to try to show, even though sound is not a transverse wave, we're going to illustrate sound as a transverse wave just as a way to make life a little bit easier. And so what we're going to do is this. We're going to put a big old transverse wave right into here. And so I'll go ahead and draw that in there. And this position right here, and I didn't draw it real well. I meant for these two to line up a little bit better. But this is a place where you'll have a node. And a node corresponds to where the molecules are basically at rest. And way over here, okay, where it's going to be flip-flopping back and forth, we'll have an antinode on this side. Let's see if I can zoom that in a little bit or focus it better. And we'll put an antinode on this side. So where the pipe is open, we have an antinode on one side and an open pipe and an antinode on the other. Right in the middle, we have what's called a node. Alright, now, next thing. There is a website, and if you want to go to this website, it's right in your packet. It does a marvelous job of illustrating this relationship, and I can't do it justice, but it does a marvelous, marvelous job. Alright, next page. Trying to move along pretty quickly here, or as quick as I can. When you blew over or blew into the straw, a standing wave is produced in the air column. In the case of an open pipe, the air molecules at the open end, okay, so here is the open end here, here's the open end here, okay, the air molecules, and let's see if I can pull this out just a little bit more, okay, and draw the so we're going to illustrate this, even though it's not transverse. We're going to illustrate with a transverse wave. This is our node. This is our antinode. Antinode. So in the case of an open tube, the air molecules at open ends move back and forth, forming a vibrating air column. And that's what we have going on here. So air molecules here are moving back and forth a lot. Here, they're essentially at rest right in the middle. All right, at the ends of the straw, the amplitude of the wave is as large, there it is, as large as it can possibly be. This large amplitude is called an antinode. Antinodes are locations of constructive interference. Okay, and we've talked about that in our last unit. At the point in the middle of the column, right here, point in the middle of the column, the waves cancel out and produce a node. And nodes are locations of destructive interference. That's why it's at rest, right there. When a standing wave is produced in an air column, a half, and this is going to be really important, I'm going to circle this, a half wavelength is produced in the air column. And we're going to use that to do example number 1. I'm moving along pretty quick, so stay with me. Example number 1 says this. If a standing wave is produced in a 20 centimeter open pipe, the wavelength of the wave in the air column is what? This is not easy, so tune in with me as we go through this. I'm just going to replicate what we just did. So this is open, this is open. Okay, they tell me that the pipe is 20 centimeters long. So there's my 20 centimeters. I'm going to go ahead and put my wave in there. So it's going to look like this. Bam, bam. Okay, now this is not a complete wave. Notice when we talk about waves, like on an XY axis here, let's see if I can do this well. Okay, this is not a full wave. A full wave would be a complete all the way back up, okay, to the top. That's kind of what this part is right here. So this part matches this part, and we don't have a full wave. We actually have a half a wavelength there. So if I were to kind of finish this out, it would look like this, and from here all the way over to here would be a full wavelength. Well, if from here to here is 20 centimeters, then from here to here also has to be 20 centimeters. So the whole wavelength, the whole thing all the way across is 40 centimeters right there. Now, some of you are thinking, oh my gosh, that's confusing. Well, here's your little tip, and if you can remember this one, you're in business. So there's another way of thinking about this. The wavelength of the wave, and this is going to be in an open pipe, I'll put open right here, alright, is always double the length of the pipe. Okay, it's always double the length of the pipe. So if your pipe is 20 centimeters long, the wavelength will be 40. If the pipe is 50 centimeters long, the wavelength will be 100 centimeters. It's always double, and that's how it works for an open pipe. All right, now we're going to move on to a closed pipe. And here's a closed pipe. A closed pipe is a column of air that is open at one end and closed at the other end. Okay, so what does that actually look like? Well, I've got a pipe right here, and I'll try to illustrate it. So I'm going to go ahead and put the closed end over here and the open end on this side. And when we do this, well, we had, if I go back up here, we had an antinode right here at the open side, and that's true. So we're going to have an antinode down here. But at the closed end, we're going to actually have a node. And what it will look like is this. So we have an antinode over here, and then a node, I'll kind of zoom in on you, and a node right there. So where it's closed, you have a node, and where it's open, you have an antinode. Notice, there's no node in the middle. So in the case of a closed pipe, the amplitude of the wave at the open end, that's over here, of the straw is as, the amplitude of the wave at the open end, that's over here, is as large as it can possibly be, corresponding to an antinode. At the closed end, right here, the waves cancel out and produce a node. That should catch up here. So node is right there. Nodes are locations of destructive interference. Unlike open tubes, closed tubes do not have a node in the middle of the column. Therefore, a quarter. Now I'm going to circle that because that's real important. A quarter wavelength is produced in the air column. So let's compare. So a quarter here for closed, and over here it was a half for an open. Big difference on those, especially for the next example on the next page. So here it is. So if a standing wave is produced in a 20 centimeter closed pipe, the wavelength of the wave in the column of air is what? Alright, so I'm going to put closed over here, open right here. Okay, so it's going to look like this. Alright, now, quick commercial over here. So if I've got a wave, there's one full wavelength. Notice, from here to here, this is 1/4 of a wave. This is 1/4 of a wave. This part right here would be a half a wave. So now check this out. Can you see where this starts low and finishes high? See how that's a quarter wavelength, low to high? Well, here's what it is right here. This is low to high. Okay, low to high. So this is only a quarter of a wavelength. And this thing right here, this whole pipe, is 20 centimeters in length. So if I go like this, well, that gets me out another 20 centimeters. But that's only half a wavelength. I have to go on another full wavelength. So back up is another 20 centimeters. And then back down is another 20 centimeters. So, finish this off so it looks a little cleaner. I've got 20 here, I've got 20 here, I've got 20 here, 20 here. So 20, 20, 20, 20 gives me a total of 80 centimeters. So if my pipe is 20 centimeters long, my wavelength, actually a full complete wavelength, is 80 centimeters. So, boy, that was confusing. You're probably thinking, how can I figure that? Well, here's your way to cheat through it. In other words, the wavelength, think about this. If it's 20, how does 80 compare to 20? Isn't this 4 times this? So it is quadruple. Okay, quadruple. I didn't spell that right. It's quadruple the length of the pipe. And if you can remember this, quadruple for a closed pipe, and back over here, and double for an open pipe, you're in business. Alright, the last little bit. When you close one end of the straw, remember when you did this? When you close one end of the straw, so there's an open pipe. Notice the change in pitch? No. No. Okay, when you close the straw, you in essence transformed the pipe from an open pipe to a closed pipe and caused the wavelength of the wave to decrease. And if the wavelength of a wave, I lied, increase. And if the wavelength of a wave increases, the frequency will decrease. And that's what you're hearing. High frequency, low frequency. And there's the change. Good luck.